All right. Okay, we're gonna go with this group for now, especially if I can get this to behave. That's good. Okay. All right, welcome, gentlemen. So, I had a little bit of foresight. I was like, okay, let me go ahead and get everything running before I let them in, because you know how difficult it can be to push the image, but it seems like it's working. I have my confirmation. So I'm watching my stream as I stream, that's neither here nor there. Let's see, as far as announcements go, let me check one more time before, nope, that's not what I want to do. Okay. Okay, I'm not sure. So I just let someone named Quincy in, but I'm not seeing you on my roster. I thought it may have been like Quincy Jones. So, oh, there you are. Okay, I got you. There you are. I found you. Okay. One more time. Okay, you guys look good. Okay. All right. So let's see. The most pertinent announcement. So I calculated midterm grades. I want to say this group actually looked the best out of all of my classes this term so far. I mean, it's the midterm, right? So with most of my classes is pretty much like a huge gap, right? There's a pocket, there's a good amount of students that get like A's and B's, maybe like 1 or 2 C's, and then there's a good amount on the other end, like on F's, all right? So if you have A's or B's, even if you have kind of a C obviously you can push a little bit more, but A or B, like just kind of keep doing what you're doing, try to help your brothers as much as possible. But if you're like at a D or F, that usually means 1 or 2 things. One, either the student is just procrastinating, right? It's just waiting to the last minute to do everything. And you know how that goes, right? You kind of leave yourself vulnerable. Keep in mind, everything is available aside from exam 2, but all the assignments, anything I would say during the lecture is already available. I try to make everything available at the start of the semester. With technology, you got to be careful with this whole remote learning thing. You got to be careful with procrastination, because if you wait to the last minute, what typically happens is like the server slows down, something happens where it just will not work. And it's going to be completely out of your control. Like it's going to be something that, something random that doesn't usually happen. So that's the danger in procrastination. So usually either the students are procrastinating or they just don't intend to do it, right? So if you or somebody usually it's not the people that's in class, usually it's not the people that is here that this applies to, but if you know someone that's like, they pretty much just have no intent of doing the work, and they're considering withdrawing, it's a good idea to obviously chat with, consult the counselor, all right? And just talk to them before you kind of making a decision like that. So either procrastination or they just don't intend to do it. And then one other thing that tends to happen is that the students intend to do it, but they just don't ask for help, right? For whatever reasons. You just got to speak up. All right, you just got to ask for help. If you're not going to team up with a classmate, or if you're not going to ask me for questions, for help or assistance, the tutors are available. They're included in your tuition, and they should be able to help you with this. All right. You've already paid them. They're really just sitting there waiting for you guys to ask questions. You can take any of this content and sit down with the tutor and say, hey, can we sit down and work on this together? And it's okay. Like, it's okay. You really just have to ask. A closed mouth doesn't get fed, right? You got to open your mouth, speak up, and ask for help and try. Really, like, again, the intent, I do acknowledge that the rate is a little bit accelerated. So to offset the experience, what I did, again, unlimited attempts and a minimal late penalty, right? You can submit things all the way up to the last second. And it's a good chance you can get a B. It's really, really, I don't want to say it's impossible to get an A, like that 90% when it's late, but you can still get a decent grade even if you submit it late. But yeah, just take the material, collaborate. It's okay. Just try to absorb and learn whatever you can. Do the best that you can. Do your best. Okay, so the midterm grades are there. Also, more than likely, what I'll do is go through my roster and check my attendance. And if students have an excess of unexcused absences, it's a good chance that they can be booted. If you feel like you or one of your brothers might have an excess of unexcused absences, and you or your brother intends to stay in the course, they just need to communicate with me so we can try to make sure that they don't fall into that purge group. Because I just had this tendency of saying, hey, I have like five or more unexcused absences for this person, you can drop them. And then obviously that can affect the money. And sometimes the students intend to finish and they can't get back in. You don't want to be in that boat of trying to get back into this thing. And you don't really want to mess up your money. So you just want to make sure, like, just reach out to me probably at the end of class or something like that and say, hey, I just want to, if you feel like you have an excess of unexcused absences. And again, if anything does happen as a result of like a purge or like unexcused absences or anything like that, again, just reach out to me, and then we should be able to get you back in there. But again, you don't want to fall into that category if you can avoid it, right? Okay. All right. So I can't think of anything else. Let me see the time. I'll be a little bit kind today and get these guys. I usually wait a little bit longer, and I'll still check at the 15-minute mark. We got this student. Okay, this one. This one. Okay. I'll go ahead and click any extra names. Cool. Okay. Okay. All right. Welcome, gentlemen. If you're just joining us, we did just kind of go through the announcements. So, let's go ahead and get this guy. Come on. There you go. All right. So welcome, gentlemen. If you're just joining us, we did just kind of finish the announcements. I did my usual. What I went on today, started the stream and got everything running before I let you guys in. And obviously that seems like it works a little bit better. I think the system might get overrun when I have you guys in here, and then that kind of disrupts me being able to push the image. I'm gonna rely on my recording, right? So we just went through the announcements. It's a good idea to just listen to the announcements. So you might have to go back and pull the video to listen to the announcements. But we're gonna go ahead and get started. Okay, and I'll check attendance again in a little over 5 minutes. I think this is gonna be our last section in chapter 3, right? So let's just focus on this, right? So chapter 3, applications of differentiation. And I think this is going to be our last section. And I want to say that the rhythm from here until the end of the semester is basically we'll be doing one section per session, right? That's not a tongue twister. Peter Pepper picked a pack of pickled peppers. If Peter Pepper picked a pack of pickled peppers, how many pickled peppers did Peter Pepper pick? I almost made it. Anyway, red leather, yellow leather. Okay. So we have section 3.8, implicit differentiation and logarithmic differentiation. Some objectives here. We like to differentiate implicitly and use logarithmic differentiation to find the derivatives of certain functions. Okay, let me kind of give this as like a baseline for what do we mean by implicit differentiation. So So far, we've been working with functions where it was basically like y as a function of x, all right? So it might be like y equals x cubed plus 2x squared, yada, 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 right? It was y in terms of x. So now we might look at functions where it might be a function in terms of more than one variable, right? And so we're going to see, like, what if we had a f of x, we have some f in terms of x and y. How do we differentiate there, right? So that's where implicit differentiation comes in, okay? And then derivatives of certain functions, right? And so then I feel like the second one is a little bit explanatory. So how to differentiate implicitly? Differentiate both sides of the equation with respect to x or whatever the variable you're differentiating with respect to. Apply the rules of differentiation as necessary. Anytime an expression involving y is differentiated, do dy by dx will be a factor in the result. Isolate the terms of dy by dx as a factor on one side of the equation, factor out the dy by dx, and then divide both sides of the equation to isolate dy by dx. So the way that they do their implicit differentiation, anytime they take the derivative of y, they put dy by dx. I actually like to do mine a little bit different, and I might kind of just jump back and forth between their technique and mine. And I'm going to start with mine just because that's what I'm more comfortable doing it the way that I do it. And then I'll try a couple doing it their way. All right. Okay. So for instance, we have this example. We have this equation, but it's in terms of both x and y. And so we're asked to find dy by dx using implicit differentiation, and then find the slope of the tangent line to the curve at the point 0, 3. Okay. So with something like this, if we try to, like, you might be tempted to try to solve for y, but obviously, we can't isolate the y by itself, effortlessly here. So that's where implicit differentiation comes in. Now, the way the text does it, they take the derivative like normal, but whenever an expression has a y, they put dy by dx. I'm going to do that in another example. First, I'm going to show you the way that I like to do implicit differentiation. So the way that I like to do it is whenever I still take my derivative like normal, all the regular rules apply. But whenever I take a derivative, for instance, when I do that y cubed, when I take a derivative with y, I'm going to put dy next to it. Whenever I take a derivative with x, I'm going to put dx next to it, right? And then I'm going to use algebra. I'm going to treat that dy and dx as like variables, and I'm going to use algebra to isolate dy by dx. Okay, so it sounds like a mouthful. It can be interesting. So let's give it a go. And here we go. Let's go view, seamless, and let's add a page. Come on. Where are you? Right here. Okay. Okay, so for part A, I'm just going to get a copy. We have this, we have y cubed plus x squared y to the 5th minus x to the 4 equal to 27, okay? So that's just our copy, and we're gonna find dy by dx. So now in order to do that, we take the derivative like normal, all the regular rules apply. Again, whenever we take a derivative of y, we're gonna put dy next to it. Whenever we take the derivative of x, we're gonna put dx next to it, right? Okay. So with this first term, right, the derivative of y cubed is, so that first guy is 3y squared dy. Okay. So then with this next term, we have to basically use the product rule, right? Which is first times the derivative of the second plus the second times the derivative of the first. Okay. So we're going to use the product rule there. Okay. So the first is x squared. The derivative of the second is going to be what? 5y to the 4, but we took the derivative there, so we need to include dy. Okay, so first times the derivative of the second plus the second, which is this guy, times the derivative of the first is going to be 2x dx. All right, we took the derivative of x, so we put dx. Okay, and then the last part, that negative x to the 4, that derivative is going to be negative 4x cubed dx. And on the right, the derivative of a constant is 0. Okay. So now what we're going to do, I'm going to rearrange everything. I'm going to expand everything all the way out, which I think it already is. If a term has dy, I'm going to keep it on the left side of the equation. If a term has dx, I'm going to move it to the right side of the equation. Okay. So for instance, the first term has dy, so I'm just going to leave that on the left. The second term also has dy, so I'm just going to leave that on the left as well. I'm just going to rewrite it as 5x squared y to the 4 dy. Okay. So the last two both have dx. So I'm going to move those two guys to the right side of the equal sign. So if I subtract that first one, I'm going to get minus 2x y to the 5th dx. If I add that last term, I'm going to get plus 4x cubed dx, right? So notice, I got my terms that have my dy on the left and my terms that have my dx. We can go this color on the right. Okay. So now, hopefully, it should be clear if we're trying to get dy by dx. On the left, we're going to factor out dy from those terms. All right, we're going to factor that out. On the right, we're going to factor out the dx from those terms. Okay. So then we're going to get a dy here. On the left, we're going to be left with 3y squared plus 5x squared y to the 4. On the right, we're going to have dx. I guess we can leave it as negative 2x y to the 5th plus 4x cubed, right? And then it's just one little maneuver, right? I'm going to divide both sides by dx. So these guys cancel, and I'm also going to divide both sides by this 3y squared plus 5x squared y to the 4. All right, that goes on both sides. I really should do that in 2 steps, but I think you can do the algebra there. So then on the left-hand side, these two guys cancel. So then ultimately, we finish with our dy by dx equals, and what's left on the right, we have negative 2x y to the 5th plus 4x cubed over 3y squared plus 5x squared y to the 4. Bada bing, bada boom, wham, bam. Thank you kindly. All right, I feel good about that. That's my style, about like this. What's the time? Okay. So let me kind of compare this to my prepared notes. I'll check attendance one more again, and we'll keep the party going, right? And just for the sake of simplicity, I think I'm just gonna copy. I'm just gonna paste this next to, let me go view, single page. Okay. Actually, what was the other part? Find the slope of the tangent line. So this is our derivative. We basically plug in when x is 0 and when x is 3. We might as well, sure. Let's go ahead and do that part. Part B, we're asked to find the slope of the tangent line at the point 0, 3, right? So then I guess we can say the slope is going to be, we're going to have negative 2 times 0 times 3 to the power of 5 plus 4. It looks like, okay, that just kind of collapses everything right there. 3 times 3 squared plus 5 times 0 squared times 3 to the 4, right? It looks like all of this collapses to 0. So it looks like it's a flat, because this guy collapses to 0, this guy collapses to 0. 0 divided by any non-zero number is 0, right? because the denominator I think is like 27. This guy goes to 0 as well, but the denominator ends up being 27. So then 0 over 27 is just 0. Okay. We're going to go with this. Hopefully I didn't make any mistakes. Okay, so again, let's compare this to our prepared notes. And is that it? That looks like it's it right there. Let me paste. And let's do it like this. There we go. So we can do a side by side. 4x cubed minus 2xy to the 5th over 3y squared plus 5x squared y to the 4. Okay. So we got that correct. And then you see the slope there, 0 over 27, which is 0. Okay, let me check on you. Zoom. I'll go ahead and let him in. And I can log in here. Cool. Another thing I did to kind of help with the flow, I put my attendance roster on a different device. So there's less on my streaming device. There's less power, less processing power and all that. So it can run a little bit more smoothly. Try to have as many things closed as possible. Okay. All right. All right. That was fun. Let's go on to the next one. Again, if anything is not clear, if you have questions, all you have to do is stop me and we can go back and talk about it. But yeah, let's keep going. Okay. Quick checks I usually leave as an exercise for you, and we have this example too. For the domain equation here, differentiate implicitly to find dp by dx. All right. So we still work in the same way as if it was dy by dx, and we're still going to use that technique that we did, right? Whenever we take a derivative, like if we take the derivative of x, we put dx. If we take the derivative of p, we put dp, and then we're going to use algebra to get dp by dx. Okay. So I usually like to start with a copy of the original. Square root 200 minus p cubed. Okay. So if we take the derivative on the left, the derivative of x is what? 1. 1 times dx is just going to be dx. Okay. Now on the right, we have to use the chain rule, rewrite that radical as a rational exponent. So when we take the derivative there, square root is the same as to the power of a half. So when we take the derivative, the 1/2 comes down, the inside persists. Then we got to say times, we got to subtract 1 from the power, which gives us a negative 1/2. Then we got to say times the derivative of the inside, and that's going to be a negative 3p squared. But then we also, because we took the derivative of p, we need to put dp. All right, that's the only thing that's different, right? So we're asked to find dp by dx. So that means we need to divide both sides by dx. And, basically multiply by the reciprocal of this fraction, okay? So if we divide both sides here, let's just kind of rewrite what we have before we do our division, okay? That negative exponent moves that guy to the denominator. So then we have 2 times the square root of 200 minus p cubed. Go ahead.
So the way you differentiate for the x is that you use the chain rule?
Yeah, on the right-hand side?
Yes.
Yeah, chain rule, right? So give me just a moment. Let me finish this out and then I'll come back to that. If we want dp by dx, I can divide both sides by dx. So we'll get our dp by dx, and then we multiply both sides by the reciprocal, right? Because basically what I'm doing is I want to move the dx over here, and I want to move this guy to the other side. So, we could divide by that, but dividing by a fraction is the same as multiplying by the reciprocal. So long story short, we get that our dp by dx is going to be, on top we got this 2 times the square root of 200 minus p cubed. It's going to be negative over 3p squared. Okay. Yeah, I think that's it. Yeah, I'm going to go with this. Let me just check that this is correct, and then we can go back and address the question that was asked. Okay. You see it there, 2 times the square root of 200 minus b cubed over the negative 3p squared, right? Okay, I think we're good to go there. So again, to kind of recap, here was just a copy of the original, right? So when we took the derivative, right, first we did the left-hand side. The derivative of x is going to be just dx, okay? On the right, we use the chain rule. So first thing that I didn't show, I rewrote this guy with a rational exponent, 200 minus p cubed to the power of 1/2. So then I took that derivative where the half comes down. You see the half here. Subtracted 1 from the power. You see it here. This persisted. Then we had to say times the derivative of the inside ended up being negative 3p squared. And because we took the derivative of p, we added on this dp. So then what we did was rewrote that guy just so we can account for this negative exponent. So this line is a repeat of the above line. It's just in a different form. So then we use algebra, divided both sides by dx, and multiply both sides by the reciprocal of this fraction. And that's how we got our result. Okay. I mean, it's fine. It's the same thing. Okay. Yeah. Okay. Let's try another one. Okay, this one looks interesting, right? Example 3, given this function, we're actually find dy by dx, right? So you just got to take your time. I think I'm gonna give myself some space. I'm gonna go view seamless, and I'm gonna add a page just to give myself some space so I'm not trying to cram stuff. Okay. We're asked to find dy by dx. And I'm going to start by just getting a copy of the original. So we have this y equals, we get x to the 4 plus 3x minus 1 quantity cubed times. We got the square root of 1 minus 3x to the 5th. Okay, and we're asked to find dy by dx. Let me think for a second. Okay. All right, so let's just kind of take our time. I was just trying to make sure that, like, think to myself for a moment to see, are there any like tricks here? I'm not seeing anything other than just what we've been doing. So we're just gonna kind of go like that. Okay. I guess this is a good one where to do it the way that the text does it. So we're still going to take our derivatives like normal, but the only difference is so the way we've done it so far was the way I like to do implicit differentiation, where whenever we take a derivative of a variable, we put d that variable, right? If we take the derivative of y, we put dy. If we take the derivative of x, we put dx. So now the other technique is whenever you take the derivative of y, you put dy. Sorry, you put dy by dx. Whenever you take the derivative of x, you just take the derivative like normal. You don't put anything. All right, so we're going to try that here because this one looks like that would be much more simple to do it that way than the way that I was doing it. Okay, so the derivative of y on the left, the derivative of y is just going to be dy by dx. Okay, so now on the right, when we go to take the derivative, the main operation is multiplication. All right, so that means the main thing that we need to do is the product rule first, right? So product rule, first times the derivative of the second plus the second times the derivative of the first, right? So let's capture that first. So the first being this, first times the derivative of the second. So I'm just going to go ahead and write the derivative of the second. So the 1/2 comes down. The radicand persists. Now it's to the power of a negative 1/2. Then we got to say times the derivative of the inside function. That's going to be what? Negative 15 x to the 4. Okay. So now before we would put in dx, but now that we're going to mimic what the book is doing, we don't have to put anything for this, right? So we said the first times the derivative of the second plus the second times the derivative of the first. Okay, so we got to use the chain rule there. I'm going to have to write on the next line, and I'm going to readjust the size. I'm just running out of space. So we're going to say times the derivative of first, right? So the derivative of first is going to be the 3 comes down. Okay, let me think about this. Yeah. X to the 4 plus 3x minus 1. And now it's going to be to the power 2. That's the derivative of the outside function times the derivative of the inside function is going to be 4x cubed plus 3. I think that's it, right? Okay. So I'm just going to, because I'm on a digital device, I'm just going to resize everything and get it on one line because I can, right? I put it on the second line because I ran out of space. So this guy, about there, right? Okay. Okay. All right. So let's see. I'm trying to see. Okay. Let's see if we can find. Give me a second. Because I could address that. Let's see if I multiply a factor. Can I multiply by 1 in the form of that over that? Okay, we can factor that out. Okay. Give me just a moment. I'm just trying to think of like what I want to do next. Because if I move that down, I can multiply by 1 in the form of, no, that's not helping. Okay, because what I'm really trying to do, I was getting a little bit stuck by, because I was focused on this guy along with this guy, right? One is in the denominator and one is in the numerator. I'm thinking like, if they were on either side of the equal sign, I think I would be good to go. But I think I'm gonna just leave them as they are for now. And let's just go ahead and factor out our common factors, right? Because we got this. Let me highlight what we have so far that's similar. So let's do this color. We got this x to the 4 plus 3x minus 1. We have one of those here, and we have another one here, right? That's not going to help that. What else do we have? We got a 4x cubed. I don't see anything else. Okay. So let's factor that out and see if we can get this, simplify this down some. So then our dy by dx, okay. Let me see. So they both have at least 2 of them. So we have this x to the 4 plus 3x minus 1 quantity squared, okay. So now in the first expression, we are left with, we have x to the 4 plus 3x minus 1 over 2 times the square root of 1 minus 3x to the 5th, okay? So that's what was left over from the first one. Nope, and I'm missing that 15, right? That negative 15 x to the 4. Yeah, let me make sure I capture that. Let's get rid of this. Nope, I do. Oh, let's get rid of this. Just gonna move this over and put the negative 15x to the 4 next to it, right? Because that persists. It's negative 15x to the 4 times that, okay? Is there one of those on the other side? I'm not seeing it. Okay. So then that was, and you know, I'm just gonna group it like this, right? Because we factored out that guy. So then we're gonna say plus, now what's left on the right-hand side? It looks like we could distribute that 3. Is there a 3? Can we factor it? We could factor out a 3 from both. Okay, let me capture that 3. Getting kind of messy. Let me capture that 3. So we can factor out the 3 from both right here. And I'll highlight it here because there's a 3 from this 15 and there's a 3 right here, right? So that 3 turns a 15 into a 5. Okay. So once we factor out the 3 from the 15 becomes a 5. The other 3 is now in front. Okay. So then now what's left, we have this 4x cubed plus 3 times the square root of 1 minus 3x to the 5th, right? You really gotta go slow and take your time. Okay. Let me look at this. Because we can combine these two. Give me just a moment. Common denominator would be that guy. So if we're looking at the two terms on the right, we can combine them. They have a common denominator. Well, we can get a common denominator. The common denominator would be this guy. This 2 times the square root, yada, yada, yada. So we would multiply the one on the right-hand side by 1 in the form of this over itself. So we can get a common denominator. We can condense this into one expression. And let's just go ahead and do it, right? And so what I'm going to do is capture it right here. It's a little bit crammed, but again, I'm going to multiply by 1 in the form of 2 square root of 1 minus 3x to the 5th over itself. Okay. So we just multiply by 1. So multiply by 1 doesn't change anything. I'm just getting a common denominator so that we can pull these guys together. Okay. I think we're almost there. I think we're close. Thank you. Stop. Okay, we're almost there. So let's try to keep going. dy by dx. This persists. I'm just leaving this stuff. X to the 4 plus 3x minus 1. I'm just letting that persist. This first one pretty much just persists as well. So I'm just going to leave it as negative 5x to the 4. X to the 4 plus 3x minus 1. I'm just going to leave it for now. Now, from this other term, we're going to have plus 4x cubed plus 3. There's a 2 in there. And the square root squared is just, I'm going to write it as 1 minus 3x, right? We're going to expand all this out, combine like terms, simplify down as best we can, and then call it a day. We're actually in the home stretch. I know it's a little bit intimidating. 1 minus 3x to the 5th. Hopefully I'm not like choosing, I might not be doing this the best way, right? But I can feel it. I'm almost there. We're going to finish it out. We're going to see the way the text does it. Maybe they did it in a fashion that was more simple, right? But what we have now all that's left is to expand that numerator, combine like terms, simplify, and go from there. Okay. So let me try to finish it out. This, that. Okay. So with that numerator, what did we do? It's going to be negative 5x to the 8 minus 15x to the 5 plus 5x to the 4. Okay, we need to distribute that guy. Okay. So what I'm going to do, I'm going to say plus 2 times. If we FOIL, that's going to be 4x cubed. Outer is going to be minus 12x to the 8. Inner is going to be plus 3. And last is going to be minus 9x to the 5th. And just for the sake of space and time, I'm going to go ahead and distribute that 2. Just going to go ahead and distribute the 2 and rewrite everything. So that 4 becomes 8. That 12 becomes 24. That guy becomes a 6. And that becomes 18. And we're going to see the way the text does it. Maybe they have something that's more concise, and we can talk about that. Okay. Okay, so that's the expanded numerator. And we're going to say over. Try to keep my grouping symbols clear. This guy's just persisting. I'm really just focused on the numerator right now. I'm just trying to simplify it all the way down. And I think we were like one step away. Combine like terms. Okay. Okay. So now we got this. It looks like a 21. Outer. No, that's not 21. That's 24, right? Outer was 12 times 2. That's a 24. Let's write that better so we can see it. Okay. So negative 24 minus 5 is what? Negative 29? I don't know. I feel like I made a mistake, but I'm going to just kind of go with it. Negative 29, x to the 8. I see a x to the 5th. What is that? 20 and 13, 33. So negative 33, x to the 5th. I only see one x to the 4. 5x to the 4. I only see the one. We got 8x cubed. And then plus 6. Yeah, I don't know. We're gonna see. This is a little bizarre. I don't think this is right, but we're gonna try to get to the bottom of this guy, right? Can we get anything else to cancel? And that guy might factor, but I'm not even about to try to attempt that. But this is as far as I would take it. I did the best I could to not make mistakes. Let's see what the text did. And they might have something that's a little bit more clean than what I did, because obviously that's intense. Is there a U substitution? If we do U du 4x, if that's U 15. Okay, let's see what the text did. Let's go to view a single page. Okay, so we got this. I'm not confident in that at all. Let's see what they did. First, I just want to see log. Okay. I knew it was something like that. I knew it. Okay. So we're going to see the technique that they used, right? I'm just trying to think. I'm not sure how and why we know to use that, but I know that makes it more simple. Let me see. Because I think we're way off, and I don't really want to attempt it again. Okay, right here. We're actually not that far off. Because I know we got that. I think we got that. But ours, we expanded and combined. If we expand this, we might get what we have. But it's not all the way there. Okay, so I can check and make sure that they're the same or not. Like for instance, I know ours is kind of bad right here. We could rationalize. If we rationalize, that's not going to help us. Nope, that's gone. It might just be wrong. Okay, I'm going to scrap it. So I'm going to put an X to this. I knew there was something. I don't know why I forgot about this, but I did forget about it. So let's see what happens, right? So here. So we have this, and we're xifying dy by dx. So then the trick that we missed, that's why I paused, and I was like, what am I missing here? Using logarithmic differentiation, start by taking the natural log of both sides, right? That was the thing that we missed. So we start here, we take the log of y, and then the log here, and when we take the log on the right-hand side, what that allows us to do from the rule of logs, that allows us to split it apart. So the log of the product becomes the sum of the logs. So this guy we're going to be able to write as one log plus another, right? Yeah, and it drastically simplifies what we're working with, right? We're basically taking the derivative of 3 logs versus what we did this giant product rule, and then the numbers just got real kooky, right? But I think it was still, the reason I kind of went with it is like it's still important that we see that. So then we're like, okay, if we come across that on our own and we're like, the numbers just seem like they're going really sideways, right? Like they did, then we might pause and say, let's come back and try this technique of taking the log on both sides, right? And so again, when we take the log on both sides, then what that allows us to do, again, on the right-hand side, the log of the product becomes the sum of the logs. And then this expression is a lot more simple to differentiate as opposed to what we were doing, right? So let's see, right? So then the log of a radical is you can basically bring the power down in front, right? So now you're just taking the derivative of these guys, which is way more simple, right? So I'm going to take the L on the other one. I was just, but I knew I was forgetting some technique, and I was like, what am I missing? But you know, again, we sometimes we need to have that experience, and then that sensation of being frustrated, and then once you figure it out, that's what puts it into your psyche. That's what makes you remember. It's like, oh, wait a minute, I remember that experience, and the solution was take the log on both sides. All right. So, okay. I low key kind of want to do it now that I know, because I knew it was something like that, but I couldn't think of to do that. I just forgot about it. Um, yeah. So the derivative of natural log. Yeah, I kind of want to do it. Is that the end? Now we saw for dy by dx. Did they do? Yeah, they kind of did what we normally do. Is dy by dx. Du over u. Did they multiply both sides by y at the end? Oh, and then they substituted back. Okay, wait. We might be able to salvage what we have. Okay. Because we have that. We definitely got that part. I don't know. Yeah, that one, right? I really don't think they were wrong. I think that we just have to like shift things around and manipulate stuff to get it to look like this. But I don't want you to kind of like I want you to kind of ignore what I did earlier. Because again, here, because our square root is over there. So if we multiply by like one, if we like rationalize, you know, we can generate this guy. I know that this guy is there, but you know, okay. But yeah, the main thing was we took the log on both sides. Now notice when we multiply both sides by y, then they reintroduced this guy. You see it here, and then they left that there. Okay. Let's see if we can find another one similar to this, and we can walk through it. Okay, but okay, so let's just kind of go with it. We're gonna let that be for now. Let's try one. Find the absolute minimum value of this. Okay, yeah, this is definitely one of those. See, this is, I thought it was gonna come up on this one. Find the absolute minimum value over of this over 0 to infinity. So, all right. So basically, they're saying what? Take the derivative, and then you know we're gonna have our derivative. Usually, when it's the absolute min or max, you also check the endpoints. But we can't check 0. But let's go ahead and take a look at the derivative, right? So again, this one is kind of similar to the one that we just did a moment ago. At first glance, you might try to take the derivative, but we haven't talked about, you know, something like this. Basically, the trick is take the log on both sides, right? So let's go y equals x to the power of x. At first glance, you're like, wait, how do we do that? So then again, we basically repeat what we did in the previous, well, what the text did in the previous, right? So we're going to take the log, the natural log on both sides. And what this allows us to happen, this allows us to bring this x out of the exponent and move it in front. Okay. So then on the left, we're going to have the log of y. On the right, we're going to have x log x. Okay. So the derivative, let me go view, seamless. Come on, stop. The derivative of log is what? Du over u. So we just saw in the previous that this guy is 1 over y dy by dx. Okay. And then on the right, now when we take the derivative, we definitely use the product rule, right? So first, being this guy, the derivative of the second, 1 over x. Okay, first times the derivative of the second, so it's going to be plus the second, which is this, times the derivative of the first, which is 1. Okay. I want to say the x times 1 over x cancel. So this cancels that. We multiply both sides by y. I'll continue working over here. So then our dy by dx is going to be, if we multiply both sides by y, we're going to have y times the log of x. But I want to say we need to substitute the y back in. So then we're going to have dy by dx is going to be x to the power of x times the log of x. Mm-hmm. So then, since we have the derivative, we want to set this guy to 0 and solve, right? To find the minimum, is because then we got to find the critical value. So let's set it to 0 and solve, right? So then, now let me think about this. Okay, I want to say that, this first expression, this guy set it equal to 0. I don't know about 0 to the power of 0, right? Any other real number to the power of 0 is what, 1? But I don't think that applies to 0 to the 0. So I'm just going to kind of like, I think that's like undefined, the x to the x. But I'm going to kind of, let me see, ignore that one for right now. And then but we can focus on the log of x equal to 0, right? Because it's basically the zero factor rule. When two or more things multiply to give you 0, you set each thing to 0 and solve, right? Let me think about this. When is the y 0? Yes. Yep. Right. So then to solve this guy, can we do that one? Let me think about it. Log of x 0. We might be able to do something with the left. I'm gonna get some help on that one. But for right now, I'm gonna go ahead and finish this one. All right. So then here to solve this guy, we're gonna say, come on, go away. We're gonna raise both sides to the power of e, so that way these guys cancel, and e to the power of 0, x equals 1. Okay, I know we got at least 1. I think that's our only critical value, and then we would test on the left and right, and it should be a minimum. So I'm gonna go with this one, right? Because we still should, like, choose a value on the left, choose a value on the right, show that the original function is going from decreasing to increasing, and then we could confirm. So with that x, finding the corresponding y is also going to be 1. So it looks like the absolute minimum is going to be this guy. Okay. Let me look at the prepared notes. Single page. Okay. So again, to differentiate, first we take the log on both sides. So we got this guy. So then, yep, we got this, right? Let's keep going. Oh, did we miss a 1? I think we did miss a 1. Okay, I don't know how I missed that. Okay, let me back up. I definitely missed it. Okay, I'm going to back up and fix that. So right here, we were on track, but we definitely made a error. Right here, right? So x divided by x is 1. So then when we multiply both sides by y, we get this, dy by dx. We're going to have y times, we missed this one right here. I'll do it in purple. We missed this guy here, 1 plus the log of x, all right? Okay. So then, should we leave it like that? Let me see. Yeah, they plugged it in. Okay, that's fine. Yeah, okay, we're good. Okay, so then our dy by dx, if we plug in for y, instead of distributing it, we just leave it as x dx times 1 plus the log of x, okay? So then for the critical values, we're going to set this guy equal to 0 and solve. Again, I'm going to kind of ignore the first one because, let me see. If we set it equal to 0, if we took the log on both sides, log of 0 is undefined. So I think this is just outside of, this is going to produce results outside of our domain, right? Because even if we set it equal to 0, here, let me just do it like this. If we did x to the x equal to 0, if we took the log on both sides, we would have x log x equals the log of 0, but the log of 0 is undefined, right? We can't do that. So then that's extraneous solutions, right? So we're gonna just say non-real solutions, or non-real solutions for that one. But the other one we can set to 0. We're gonna have this 1 plus the log of x equal to 0. Okay. Let's see. We can subtract 1 on both sides. We get the log of x equals -1. We raise both sides to the power of e, so we say e to the power of that, e to the power of that. This is canceled by that. On the left, we have x equals, and then the exact result we get is e to the -1. Okay. So with that value of x, the corresponding y, whatever e to the 1 to the power of e to the 1 is, a power to another power you multiply. So e to the negative e to the -1. Let me go with this x. Let's go back to let's finish out with the pair notes. Okay, so where we left off, I think we got all this. I think we were good there. Right? We realized that we missed this one, so we went back and accounted for it. We got to this point, right, when we substituted in our y. So then when we set it to 0 and solve, okay, we can ignore this factor since it never is going to be 0. Right? So it's a similar thing similar conclusion that we came to, right? So we can ignore this because it's never going to be 0. So then we just set the second one to 0. Again, e to the -1 was this guy. Again, we just didn't crunch that number. We left it exact. Okay, so then, that was it? No. So using the first derivative test, so you want to choose something on the left, choose something on the right, and show that the original function is going from decreasing to increasing. Or you can use the second derivative test, and as long as it's positive, if the second derivative is positive at this critical value, that means the original function is concave up, which means that we're working with a minimum. So then, and then basically when you plug in e to the -1 into the original, this is the output. We just didn't use our calculator there, right? But we knew to do that. So then, by either the first derivative test or the second derivative test, you can say that that's indeed the absolute minimum from 0 to infinity. Okay. And basically, again, let x be e to the -1, and then plug that into the function, and that's going to be your absolute minimum. That was an adventure. Oh, that was the end. And we got a solid 15 minutes. Okay. With the solid 15 minutes, I want to take some time and I want to look at the homework for this section. I just want to take a look at it. We could go back and look at some of these examples as well, but I want to just take a minute or two to kind of look at the homework, just to kind of get a sense of some things here. Let me go ahead and add a page. And let's just do a few examples. I won't keep you more than like about 10 minutes. Let's go view, seamless. Okay. Get rid of that. So that's not bad. I mean, yeah, I don't know why I didn't even think to, like, I knew that was coming and I'm like, just use the technique. I was like, no, it's not time. And then I was like, oh, it was time. I was like, doggone it. Okay. Right here. Okay, let me get rid of all this stuff. I don't want to put anybody on blast. Those 9 terms. Okay, let's go here. Allow. But again, the only reason we got caught because we just forgot to use the technique. Now we're, we know that that's one of our options. If you're working a implicit differentiation and it just gets messy like it did during class, then try taking the natural log on both sides and then try simplifying that, right? Okay, let's go calculus for business. And again, I'm not trying to be rigorous here with you guys. I'm really just trying to expose these concepts and touch on things that I know we need to talk about, and then just kind of just get it submitted. Okay, chapter we just did 3.8 right here. I want to kind of look at this homework. And I feel tempted to like start somewhere in the middle, so I'm just going to start in the middle because I want to kind of get to the implicit differentiation, even though I know we don't have a lot of time. Differentiate implicitly. Okay, the second derivative of y with respect to x. Okay, this is an interesting. Let's give this a go. This does look like one where we would need to take the log of both sides, right? So let me start by getting a copy. And like, honestly, if we had the time, I would go through more of the homework, but you saw how we were doing 2 sections a day for a good portion of the time. Copy and delete. It wasn't until recent that we got the luxury of doing 1 section a day. Let's paste. You want to paste for me? Thank you. Couldn't find my pen. It just like disappeared. It's a white pen on a white table, so I'm just being seen now a little bit of my young age. Okay, differentiate implicitly to find this. Okay, so basically they're asking us to take the second derivative of y with respect to x. Okay, let me think about this. How did I used to do that? There was a trick there. You get the dy by dx. Once we have the first derivative, dang, what was the technique that I used to do? Okay, I'm going to try something. So the second derivative was a little bit different. I'm trying to remember the nuances there, and I'm not seeing them all. I'm going to try it the way that I normally do it. I might run into a hiccup. I might get stuck. If I do, then I might try it the way that the book does it. Okay, so let's just give it a go. And I'm just trying to be cognizant of the time, but I'm trying to be as clear and concise and accurate as possible. Let me try it my way first and see if I can get it to work. So we get this x cubed minus 3y cubed equals 2, right? So I think the first derivative is not a big deal. All right, so if we take the derivative, the first term is going to be 3x squared dx. Okay, I think that's okay. The second one is going to become what? Negative 9y squared dy, and that's going to be 0, right? The derivative of a constant is 0. So now for the second derivative, I'm trying to think, do I need to solve for dy by dx, or can I just do it from here? That times the derivative of that. Let me see, this times the derivative of that. When we take the derivative there, what's going to happen? I don't want to look at that. This times the derivative of that plus this times the derivative of that. Okay, give me just a second. I want to look at. Oh, I was trying not to do this. Let me think what I'm going to do. I could solve for dy by dx and then just take the derivative again. That might be the most simple, because there's a different way that I want to do it, but I'm missing something. So I'm going to do it the way that I think will work, right? So what I'm going to do from here is go ahead and solve for my dy by dx. Let me see. Okay. Let me try something. I'm going to do this in purple. Let me see something, see if it works. So if we focus on this guy, right, and we're taking the derivative of this, Let me think. First times the derivative of the second, what is that going to be? Is that a constant? Do we treat it like a constant? Let me just do a quick search. Give me a moment. We still got a solid 5 minutes, a little over 5 minutes. So let me just do a quick search, see if I can find it real quick what I'm looking for. I'm going to do implicit. Can't spell for some reason. Second derivative. There it is. Implicit derivative. And where is it? Second derivative is this one. Let's see what happens. Oh, yes. Yes, I remember that. Don't forget to plug the first derivative. Yep, I get it. Can I just see one worked out? I don't want to watch a video. The first derivative is fine. They get that. That's fine. So the second derivative, bottom times the derivative of the top. Okay, we might need to do it that way. Bottom times the derivative of the top minus the top. Yeah, I think we're gonna have to do that. Is there another way to do this? How did they do it here? Okay, that's fine. Okay, let's see. Second derivative, bottom. It's right there. Times the derivative of the top. Yep. Okay. Okay. So I think we're gonna have to do this one, at least for right now. We're still at the level of having the first derivative. So let's go ahead and find our dy by dx, all right? So if we move the term with the dy to the right, using algebra, we're gonna get 3x squared dx equals 9y squared dy. And then use algebra, divide both sides by dx, divide both sides by 9y squared. So then dy by dx ends up being, we got this 3x squared on top and 9y squared on bottom, all right? So now, come on, there it is. When we're going to take the second derivative, so that's going to be the second derivative of y with respect to x, okay? So now we take the derivative again, but now we're going to use the technique the way the book does it. So whenever we take the derivative of x, you just do it like normal. Whenever we take the derivative of y, we're going to put dy by dx, okay? So we have to use the quotient rule. So that's going to be the bottom, which is this guy, times the derivative of the top is going to be what? 6x. So the bottom times, so low d high minus high d low. The derivative of the bottom is going to be 18y. But remember, we just took the derivative of y, so we need to include dy by dx. Okay. Low d high minus high d low all over the bottom squared. 9y squared squared. Okay. Okay. So then, let me see if we can get anything to simplify. 9y squared. Okay, let's go ahead and incorporate. So now we got this dy by dx. So that means plug in the first derivative, right? That's what that means. So then the second derivative of y with respect to x. So I'm going to leave it as 9y squared times 6x. This is going to be it, and I'll get you guys out of here. Minus 3x squared, 18y. Now dy by dx is this 3x squared over 9y squared, okay? So I just plugged in the derivative there, and then we got the 9y squared squared, okay? Let's see. Maybe I can clear out the fractions. I got a cancellation that's happening. For instance, this 9 turns this 18 into a 2. This y gets rid of one of those y's. I was kind of hoping I can factor something out, but it looks like it's gone. So I'm just going to expand and simplify. I was going to factor, but now I'm just going to expand and simplify. Okay, so we get 54 y squared x. Let's see. 6 times 3 is 18. minus 18 x to the 4 over y. I know, I'm getting them out of here. Stop. And then all over, okay, we got this 9y squared squared. And then to get rid of that complex fraction, which is the fraction within the fraction, we're going to multiply by 1 in the form of y over y, okay? So then what happens there, if we distribute the y on top, right, what's going to happen, we're going to say this times y, this times y. So then we get 54y cubed x minus 18 x to the 4y, okay? Actually, no, because it's going to cancel this guy right here. So the whole point was to get rid of that fraction, so that cancels, so it leaves us with this. And then on bottom, looks like we have what, y to the 4, so now it's going to become y to the 5th. So 81 y to the power of 5. Is there a 9? We can factor, we can did I miss something? I feel like I missed something. Hang on. 6 times 3 is 18. Yeah. Right. So we can factor out a 9 from everything on top. Okay. We're gonna cross our fingers and submit this final result and get you guys out of here. Hopefully we caught everything. We can factor out a 9 from everything. So then it's gonna become 6y cubed x minus 2x to the 4 over 9y to the 5th. Okay. Okay, I feel good about this. Come on. I'm going to submit this on Pearson. Hopefully it's correct and we can get you guys out of here. But yeah, it takes a little bit of effort. You just gotta go slow, take your time, give yourself plenty of time, as much time as possible, you know, to think about this stuff. And it's also recommended that you kind of do it when you first wake up. Let me submit this to see if it works. Right here. Where'd you go? This one. Come on. I'm just trying to see my enter while I type it. That's good. Okay. Come on. Turn this off. All right, we're gonna cross the fingers. Let's see, let's do a fraction. So we got 6y cubed, 6y to the power of 3, x minus 2x to the 4. And on bottom, 9y to the power of 5. Awesome sauce, right? So I'm glad we did that, right? So the takeaway there, let's just do a quick recap and I get you out of here. So we did implicit differentiation, like whichever one you're comfortable with. And then we got this final result of, we got the first derivative, right? So we went on our first derivative, we got here, then we stopped. So then for the second part, you take the derivative of that. So then the dy by dx just became, you know, the second derivative of y with respect to x. And then on the right, you take the derivative like normal, but the only difference is whenever you take the derivative of x, you just put your answer. But whenever you take the derivative of y, you put dy. And it only occurred once when we took our second derivative. So then from there, on the next line, what we had to do was plug in our dy by dx. Not there, but we basically have to plug in our dy by dx there. And then through algebra, taking your time and techniques, simplify it down to here, okay? All right, guys, you guys are awesome. I feel like there should be questions. Obviously, you know, if I've made those kind of mistakes on like a couple of, it's gonna be there, right? Use your resources, work together, ask me questions. I know I have at least one student ask me questions. It's been years since I had a student ask me questions, so it's so refreshing. I encourage it. For right now, for the rest of the day, I would just like zen out, eat some food, get some rest, go to sleep, play some games, go outside, enjoy the sun, and then when you go to sleep and you wake up, especially if you wake up at like 3 or 4 in the morning, that's when I did all my studying. That's the best time to look at this stuff. That's when your mind is the most crisp and fresh and clear. Now, obviously, that's if you're by yourself. If you're working with people, then you do the best you can there. Um, yeah. Would anybody like to ask any questions before I let you guys go? Going once, going twice.
Uh,
Yes.
I just have some homework questions.
Sure. We could definitely talk about it. Anybody else have any other questions before I release the group? Going once, going twice. Okay. Aside from these homework questions, we're gonna hang around and stay on the stream and kind of work on some homework. But if there aren't any burning questions, we're gonna go ahead and officially end the session here. And from one beautiful mind to another, I see you guys next time. Okay. You're more than welcome to stay on the stream. We're just gonna kind of work some questions and get through as many together as we can. Okay. I know you emailed me like before. You want to just like resend those questions? Like whatever is fresh, just like send it now.
Yeah.
It's like, yeah, I'm not sure if you like answer some of them or not, or but yeah, I like these. Like and the only reason like I would miss the stuff that I miss is because I don't do it every day. All right. But I'm aware of it. And so I was like, wait a minute, what am I missing? And I knew it was, I just forgot about it. I was like, but it's okay. Yeah. And with these, and I'm just kind of filling the air until like the questions come. Matter of fact, let me pull it up here. What I was kind of sharing with like some of my college algebra students, mathematics is, and I consider it an art form. Give me just a moment. Oh, good chocolate. I consider it art, but I was sharing with them, I was like, this is the art of patience. You got to slow everything down when you're doing this stuff. And I don't expect the average bear to do that. Because in this day and age, a lot of people have the microwave mentality. They're standing in front of the microwave with their arms crossed, like, can you please hurry up? It's a microwave. Like, it don't get much faster than that, right? So a lot of people in this day and age don't have patience. So the nature of this, and just, I'm just filling the air until those questions come through. But the nature of this, you got to slow it down. Take your time, space it out, be neat and organized as best as possible. Because if you don't do those things, it drives you insane, right? You got to like just, put on some relaxing music, something real soft in the background. Just take your time, line by line, step by step. If you can't slow down, it's not a good idea to look at this stuff, right? Minimal to no distractions, that kind of thing. Let's see. But yeah. And I'm thinking back, man, I survived this class. Like the last class, man, I was like throwing up a lung. I was like, oh my goodness. But I knew exactly what it was. Like I said, I was in the middle of a fast. And let me pull up this question. And I overdid a natural herb foolishly. So, when you do stuff like that, you get the results like I got. I'm just going to start with the first one that you sent. Let me see. So, find the absolute max and min values. Where does this come from? 3, 4. Okay. Let me share. Okay. So find the absolute maximum and minimum values of the function. So this question comes from 3 for question 18. Find the absolute max and min values of the function over the indicated interval and indicate the x values at which they occur. So between -8 to 8. Okay. This. I'm going to get a copy. Get rid of this. We can get rid of this. I'm going to copy and delete. Let's hop here. Got that. Let's see what's going on here. Let's paste. I need to go through and update my my YouTube studios. Just go through those and organize. Maybe I'll do that. I feel like I got energy today. I might do that today. Find the absolute max and min. So then that means basically they're asking us to look at the first derivative, right? So let's take the derivative. Okay, so then f prime. The two-thirds come down. And I have this x plus 4. If we subtract 1 from the exponent, it's going to become a negative 1/3. Is that a minus 6? It doesn't matter because it's when we take the derivative, it's gone. So then we want to set this to 0 and solve. So this right now at this stage, we have the cube root of x plus 4 times 3 under 2 equals 0. All right, I'm basically just accounting for that negative exponent. Okay. So then we want to find the values of x that either makes it 0 or makes it undefined. And the value of x is going to make it undefined is if we set the denominator equal to 0. Okay, so let's just set the denominator to 0 and solve. So we have this 3 times the cube root x plus 4. We're going to set this guy equal to 0. We can divide both sides by 3. And okay, that's going to give us the cube root of x plus 4. We can cube both sides. X plus 4 equals 0. Subtract x equals negative 4. Right? So it looks like if we let x be negative 4, it makes our first derivative undefined. So this is going to be our candidate for a critical value. So then what we need to do from there is put it on the real number line. And again, we're looking at f prime. This makes the first derivative undefined. So we need to choose a value on either side or look at the second derivative. I'm just going to do my first derivative test. So then, for instance, if we plug in negative 5 into the first derivative, we can plug it in here. If we plug in negative 5, cube root of negative 1 should be negative 1. Ultimately, the first derivative is going to be negative, which means our original function is decreasing. Okay, if we put in something to the right, like maybe if we do negative 3 into the first derivative, if we plug in negative 3, this thing is going to be positive, right? Which implies that our original function is increasing. So that implies that when x is negative 4, we experience a local minimum. Now, if we want the absolute max or min, the only other thing, so we just basically need to test our critical value and the endpoints, right? So what we're going to do is make a table x versus f of x. The endpoints are what? -8 and 8. And our critical value is what? -4. Let's just keep this in order. -4 and 8, all right? So then we need to plug these guys into the original, and the absolute minimum is going to be the value that has the smallest, and the absolute max is going to be the largest. Okay, so what I'm going to do, I'm just going to use my calculator. Come on. My device is kind of going on a tangent. Come on. No, you're the main one that needs to work. Come on. Okay, what if I go like this? Ooh, come on. Go away. Open up. Do something. I can't get this to go away. So that probably caused my image to go away. So now I got to try to bring my image back. Zoom. Okay. Let me share my screen. Start the broadcast. So right get this to work. Maybe it's sometimes it also throws attention when I have it plugged in. Oh, my device is just throwing attention. It's really messing me up. But now I'm just trying to get this thing. Come on, I need you to do something. Come on, go away. What is this thing? My device is like, no, I don't want to work right now. See if I go like this. No. I can't get it to go away. Okay, all right. Let's try this one more time. Nope, that's not what I'm trying to do. Yeah, it looks like my just being pushed. What I'm trying to do is pull up my calculator. Right there. Okay. Let's open up a new right here. Okay, that looks good. Let's quit. What I'm going to do, I want to find those values. So I'm going to go to my y equals, and I'm going to put in the original function. We got this x plus 4 to the power of 2 over 3. Okay. All right. So then we can just look at the table, I guess. That'll work, I guess. Table. So then when x is -8, I mean, that's fine. We'll take the approximation. Let me see, how do they want the final answer? Round to 2 decimal places is needed. The absolute maximum value, okay. Okay, let's fill in this table. So when x is -8, we get 2.5198. -4, we get 0. And when x is 8, we get 5.2415. Okay. So I think the x for the absolute max. So then here's our max value, and here's our minimum value. Okay. So then if we hop back here, this one, the max was the we get 5.2. It says round to 2 decimal places, so 5.24 when x is 8. Okay, what was the maximum value that we got? Correct answer, 8. Wait a minute. Let me see. When x is equal to, did I type it in wrong? Let me go to my y equals. X plus 4 to the power. Oh, I forgot about the -6. That's what it is. I don't know why I'm not seeing that -6. -6. Now I feel tempted to do another one. Well, we can just confirm the number, right? We just forgot the -6. So then, stop. We should go back and let me just do a similar one because I just forgot about the -6. Can we? I think we can pull the same one back up. Give me just a moment. If I go, I'm gonna close this out. If I go here like this, it should be the same. So we can kind of, I just want to work it from the beginning. Should be the same one. Okay. So again, the only thing we were missing was the -6. So then now when I go look at my table, we need to update our results. So -8, and let's hop back here. Oh, good. -8, we get -3.4. At -4, we get -6. And then at 8, okay. At 8, we get -0.7585. So then I think that's still our max, and I think we still have the same max and min, just different values. Okay. Again, that just happened because we were missing the -6 when we typed it in the calculator, and I think that that's what they had. So we can go ahead and submit that result. So the max value was that -0.75, 2 decimal places, 0.76 when X is 8. Okay. And then the minimum, I think, was when X was -4. We had -6. So -6 at X equal to -4. Okay. Is that okay? Did you have any questions there? Before I go on to the next one.
No.
Okay. So let's do the next one. Yeah, I think that was it for that. Okay. So then here, the next one is, yeah, let's talk about this here. Okay, we can go full screen with this. Let's just put this here. Right there. We can suppress that. Might have too many windows open. Okay. So this comes from 3.4.35. It says find the absolute extrema of the function if they exist over the indicated interval. Also indicate the x value at which each extreme occurs. If no interval is specified, use the real numbers all rails. Okay. Let's get a copy. I'm gonna crop here, here, copy and delete. I'm gonna drop the copy here. And let's paste. That looks good. All right. So you're good here. Extrema, right? So we're looking at our derivative, right? So f prime, the 1/9 comes down, x to the power of -8/9 Okay. So this is really you can look at it as the ninth root of x to the power of 8. There's a 9 here, like that. We're setting this to 0. This won't be 0, but we also want to consider values of x that make the denominator, that makes this undefined. In other words, that makes the denominator 0. The denominator is going to be 0 when x is 0. So our candidate for our critical number is going to be x equals 0. Okay. So we want to choose test values on the left or right of 0. Again, when we plug 0 into the first derivative, it makes it undefined. So left, we can plug in -1. If we plug in -1, it becomes positive, and then it stays positive, right? So we get to the first derivative is positive on the left of 0, which implies that the original function is increasing. On the right of 0, if we plug in a 1, I think we also get a positive as well. So same deal. So then that means that 0 is not an extrema, but we still test the endpoints, right? If we plug in 0, so then if we test the endpoints, when we plug in 0, we get 0. The ninth root of 512 is probably like 2 or something. Let me see. So yeah, let's do -512 to the power of 1/9. -2, right? Okay. So if we make our table like we did in the previous, our x versus our f of x, normally that 0 would not be a critical number, but because we have closed endpoints, we're testing our endpoints. So when x is a -512, and when x is 0, we know that when x is 0, y is 0. When x is -512, the corresponding y, I think that was -2. The maximum value, this was our max, and this was our minimum value. Okay. So I think we have everything to answer the question. Okay. This one right here. You can go. Was the origin? So it's this one. The absolute maximum that we got was 0 when x was 0, and the absolute minimum was what, -2 when x was a -512. Okay, I'm gonna go with that. Okay. So did you have other questions or?
Yeah, I have other questions.
Okay. Was this okay?
Yeah.
Okay. Hey Google, change the light color to soft white.
All right, changing 4 lights to soft white.
So I need to put an application there. I'm not really taking it serious. Let's see. Sometime. Oh, okay, you sent it. Okay. Let me pull this up. Oh, there's another one. Okay, let's see. Let me just share. So we got at least two more. Okay, so maximize this. Where's this? 3.5. Maximize this where x and y are positive numbers such that x plus 9y squared equals 3. As a variable. So if q, let me see. And it says to write it in terms, write the objective function in terms of y. So we can get x in terms of y and then plug it in. If we want to maximize it, are there multiple parts? I feel like there should be other parts. Okay, so I'm going to start by assuming that there's multiple parts here, and so maximize q equal to. All right, so it looks like q is going to be equal to x times y. So we can write q in terms of y because we can write x in terms of y, right? So from what was given, if we get x in terms of y, we're going to get what? X equals 3 minus 9y squared. So then q is going to be y times x, but x is 3 minus 9y squared. If we get it wrong, we're going to go a little bit further because there's more we can do here, but I think they just want this part. We could distribute that y and expand it, but we're going to go with this for now. Okay. So again, if anything isn't clear, just stop me and we can talk about it. So then the interval of interest of the objective function.
Professor, what was the first one?
How did we get that first result?
Yeah.
So we want to maximize q, which is equal to x times y, right? But they give us the second equation that says where x and y are positive numbers such that x plus 9y squared equals 3. And they want us to write q in terms of y alone, right? So from that second equation, we solve for x. We can get x in terms of y, and then we plug that into x times y. So x is going to be 3 minus 9y squared. Then we're going to say that times y. And that's where we got that. So now basically, if we want to maximize this guy, we want to take the derivative, find the critical values, and find the critical values in the extrema. Okay. So let's take some notes.
Professor,
Yeah.
you said for the first one, we're trying to uh,
Let me write it out. I'll write it out. Let me just write it out. We'll get this. Let me copy and delete. Here. Let's paste. Okay. Okay. So again, they're asking us to maximize Q, which is equal to X times Y. They tell us the X and Y are positive numbers such that X plus 9Y squared equals 3. And so the first thing they ask us to do is basically write Q in terms of Y alone, right? Right now, Q is in terms of X and Y. They want us to write Q where it's only Y, all right? So what we're gonna do, what we did was solve for X from that second equation. If we solve for X from that second equation, we're gonna get X equals 3 minus 9Y squared, right? And then substitute this X into Q. So if Q is gonna be X times Y, then that's going to be this 3 minus 9Y squared times Y. So that's how we got Q in terms of Y. So then if we want to maximize this guy, basically we want to look at the derivative and then find the critical values and find our local extrema, right? So then I'm going to rewrite Q. I'm going to distribute that Y. We get 3Y minus 9Y cubed, right? I just distributed the Y. And now I want to look at Q prime. So now we're going to take the derivative. The first one is just 3. Next one is going to be what? 27Y squared. Okay. So then what we want to do is set this guy equal to 0 and solve. Okay. We can add that 27Y squared to both sides and we'll get 27Y squared equals 3. Divide both sides by 27. So then Y squared equals, what is that, a 1 by 9? So when we take the square root, Y equals plus or minus a third. So then we have two candidates for our critical values that we need to test because we're trying to find the max, all right? So we're going to put those on our number line. We got a negative 1/3 and a positive 1/3. And we want to evaluate these in Q prime. And again, this is like our Y over here. I know it's a little bit weird because of the, but just we're working it the same way. The labels are just shifted around. So these both should make the first derivative 0. Left of a negative 1/3 is something like what? 1. So if we plug 1 into the derivative, negative 1 into the derivative, we're going to get a negative result, right? Because negative 1 squared is positive. 3 minus 27 is going to be negative. So everything to the left of this guy should make Q prime negative, which implies that our original function is decreasing on the left side of this guy. Between negative 1/3 and 1/3, I'm going to plug in 0. So if we plug in 0 to the first derivative, we get a positive result. All that's going to be left is that 3. Okay, so we get a positive result, which means the function is increasing between these two critical values. And then to the right of 1/3, we can choose something like 1 and plug it into our first derivative. And I think it's the same argument. We're going to get a negative, just like with the first one. So we're going to get a negative result over here, which means that the original function is decreasing. So then if we want to maximize, we have a local max when Y is a positive 1/3. So then we take that 1/3 and plug it into Q. So we're making our table Y versus, I'm going to write it as Q of Y because that's what we're doing. And the only one that we're really considering is the 1/3 because the other one is a minimum, right? So when we plug 1/3 into Q, let me, I'll just take this one. Let's copy, paste. So when we plug 1/3 into there, Q of 1/3 is going to be 3 times 1/3 minus 9 times 1/3 cubed. It's going to be a 1. So we got a third times a third times a third. So that's a 9th times a third. So that's ultimately just a third. All right. So 1 minus 1/3 is what? 2/3. Let's write that to a little bit better. Two-thirds, okay. So this is our max from the first derivative test. Okay, let's see how to. Let's see. So we got a maximum value of 2/3 when Y is 1/3. Okay, let's go back. The interval of interest of the objective function, maximize this, where these are positive numbers. It's either going to be 0, I'm thinking like 0 to infinity or all rows. Oh, we don't have a view and example. Type your answer in interval notation. Because it says we're working with positive numbers. Let me try 0 to infinity. This one I might not get right. Let me think about it. Let me. I feel like it should be 0 to infinity. I'm going to kind of guess and check here a little bit. 0 to infinity. Read the problem statement to find out what values are permitted for X and Y. So maybe it should be, so if they're positive, maybe we just need to do, instead of a square bracket, do a parentheses. Yeah, okay. Because they're positive, so they can't be 0, right? Okay. Okay, so the maximum value of Q, we got a max value of 2 by 3, 2/3. And that occurs, oh, well, that was it.
What's that?
Yes.
What does the second solution say?
The interval of interest.
Yeah.
So that was based on the conditions or the parameters given, right? Because it says that X and Y are positive numbers. So then, we're only considering basically 0 to infinity with the half interval 0 to infinity, or the open interval 0 to infinity. In other words, that 0 needs a parentheses and not a square bracket.
Okay,
Is that okay?
So it's like parentheses 0, comma, infinity, parentheses.
Mm-hmm. But that comes from, because it says that X and Y are positive numbers. If it said non-negative, then that would be a square bracket. But since it said positive, that means it needed to be strictly larger than 0.
Okay, and the maximum value of Q is 2/3.
Mm-hmm. So that came from what we did over here, right? Let's kind of recap all of this. Let's kind of go through this one more time. Right here. So to kind of go back, let's see, right here. So I think it's okay. We're okay with how we got Q in terms of Y, right? I think that was okay because we went through that. So we were asked to maximize Q, which is X times Y. We were also given the second piece of information that X and Y are positive numbers such that X plus 9Y squared equals 3. And they asked us to find Q in terms of Y. So we solved for X and we got X in terms of Y. So then what we did, we took that and plugged it into this guy and we got this, right? We replaced the X. So you see the 3 minus 9Y squared, this guy. Okay. So now we got Q in terms of Y. So then from there, we went on and took the derivative, right? So from there, we took the derivative. Derivative of 3Y was just 3. The derivative of negative 9Y cubed, the 3 comes down, was negative 27Y squared. So then now that we have Q prime, if we want the maximum, that means we need to, so we set it equal to 0 and solved, add the 27Y squared on both sides, we get this guy, divide both sides by 27, we get this, take the square root. Now, when we took the square root, whenever we take square root, we're supposed to do plus or minus. Now, that minus 1/3 is actually outside of our domain because we said we're working with positive X and Y. So we really didn't have to test the negative 1/3, but I just went with it, right? Because again, the negative 1/3 is outside our domain, but I don't think we realized it at the time. But we caught it in eventually. So we did have a minimum, but we weren't concerned with the minimum. We wanted the max, right? So we put our candidates on the number line. We did our first derivative test. We got that the original function went from decreasing to increasing to decreasing. So since we wanted a max, that means we need to consider this guy. Okay. And with the when Y was 1/3, the original function goes from increasing to decreasing. So it's a local max. So then from there, we plug the 1/3 into the original. And when you plug 1/3 into the original, the output is the 2/3. And so that's where that came from. Is that okay?
Yeah.
Okay. I think we had, let's pull up the next one. This one here. Let me share. Okay, let's take a look at this one. So we're asked to find the maximum profit and the number of units that must be produced and sold in order to yield a maximum profit. Assume that the revenue and costs are in thousands of dollars and X is in thousands of units. So we have this revenue function, cost function, and we're asked to maximize the profit. Okay, we got it. Get a copy. Copy and delete. Gonna hop over here and paste. I like that. Okay. All right. Maximum profits, right? So first thing is what? Right here. Profit is what? Revenue minus the cost. All right. So fortunately, they gave us our revenue function, our cost function. So let's do that calculation. That's going to be this 9x minus 3x squared minus, we got this x cubed minus 5x squared plus 2x plus 1. All right. And we want to maximize the profit. Let's expand this out, simplify, combine like terms and simplify. So we're going to get this 9x minus 3x squared minus x cubed plus 5x squared minus 2x minus 1, right? I'm going to combine like terms and put it in descending power order. So then I get my negative x cubed. You got negative 3 plus 5 is going to be plus 2x squared. You got 9 minus 2 is going to be plus 7x and minus 1. This is our profit function. Okay. So just like in the previous, if we want to maximize this guy, okay, if we want to maximize, basically what? Take the derivative, set it, find the critical values, use the first derivative to find the maximum value, right? So then we're going to look at P prime. So when we take the derivative, we're going to get negative 3x squared plus 4x plus 7. Okay, so it's basically an upside down parabola, which is a good omen. We're going to set this to 0 and solve. But we could use the vertex formula to jump straight to the vertex. We could use the quadratic formula to get to solve this guy. We want to find the x that makes this 0. Feeling like the quadratic might be the most simple way to go here. I think I'm gonna use the quadratic formula. Okay, so quadratic formula. The negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks, and it was all over by 2 a.m. I had a student show me that in the past. It instantly was like, seared into my mind. So it was just an interesting way of remembering the quadratic formula. So that's how I remember it. Okay, so then we're going to plug in the different components. So negative 4 plus or minus the square root of 16 minus 4 times negative 3 times 7 all over negative 6. Negative 4 plus or minus, that's going to be positive. 21 times 4 is what, 84? 84, 94, 100, right? So the square root of 100 over negative 6. Negative 4 plus or minus 10, negative 6. That's going to be 14 over 6, or 10 minus 4 is what, 6? 6 over negative 6 is negative 1. Go a little bit further. 7 over 3, or negative 1. Okay. So these are our candidates for our critical value. All right. So both of these should make the first derivative 0. Okay. Negative 3 minus 4 is negative 7. The negative 1 works. 49 over 9. I don't feel like doing all that. I'm just going to assume that it works now. Okay. But both of these should make the first derivative 0. So then we need to do our first derivative test to see which of these is the maximum. Okay.
Okay.
And then again, it's the same kind of argument as before, where we're not going to produce a negative amount. So, we should be limited. It should really just be the 7/3. Am I doing this right? because that wouldn't make that result wouldn't make sense. But I'm going to just go with it anyway. We should be just dealing with the positive outcomes, because if the result were negative 1,000, that doesn't make sense in the context. We're not going to produce a negative amount of units, right? It doesn't make sense. So I'm really just going to go with the 7/3 and confirm that that is a max. Now, and remember, this is in thousands of units, right? So we'll make that adjustment momentarily. 7/3. We're going to compare this to P prime. It should make the first derivative 0. Again, we're just confirming that. Now we could look at the second derivative. That might be simple. Let me go ahead and just do the second derivative over here. Yeah, let's just do that real quick. It won't take that long. P double prime negative 6x plus 4. So then if we plug 7/3, 3642 divided by 3. Just, I don't feel like doing that. 1, 12, 14. Looks like it's a negative 14. So it looks like it's going to be negative, which means the original is concave down. So that confirms that it's a max. If you plug the 7/3 into the second derivative, you should get a negative result, which means the original function is concave down there, which means that this is indeed a maximum value, right? So I'm going to just say P double prime of 7/3 is going to be negative, which means that the original function is concave down, which implies that that's a max value. Okay. So then if the 7/3, if there's a maximum when x is 7/3, then we need to find the corresponding, what that profit is. Okay. So we basically need to plug that into the original. Let me use my calculator. This one, yeah. Come on. Okay. My device is like totally throwing a tantrum. I don't know what's going on. Okay, so the original, right there. So we get this negative x to the power of 3 plus 2x squared plus 7x minus 1. Okay. I want to plug in when x is at 7/3. So 13,518 units.
That's it.
Yes.
When you're playing, are you playing 7/3 into the original P of X?
Yes. The one that we found, the original profit function. Now we have to keep in mind that all of this is in thousands of units. We get this 51851852. I'm gonna just write it like this for right now. Okay. 7, 2, 2 1/3. So 7/3. It should be. If we think about this in thousands of units, 7/3 is 2.3 bar. So it looks like 2,333 units approximately. And if that's in thousands, the profit should be $13,518.52. These are approximations. I think we interpreted this properly. So if we maximize the profit, if we produce and sell that many units for a profit of 13,000. I think that's how that goes. Let's hop back to Pearson, submit these results, and make sure that we're visualizing this properly. Okay. is this one. Oh no, did we lose our page? Maybe it's still, is it still attached to this guy? No. Maybe we lost it. Let me just open it back. Like this. Let me see. Are you coming? Full screen. Let me just close it. Let's get rid of that. Get rid of that. You can open this and then come on. I'm going to get rid of all these tabs as well. Okay. So now when I open it, should just come to. It should be the same. Okay. Do not round to the front. Then round to the whole number as needed. Yep. The max is about to the nearest whole number. So yeah, we got 2333 units. 2333. We're gonna, hopefully that works. If that don't work, we'll go back and figure out 2333. Woohoo! Okay. And the profit, that's
Professor.
promising. 13,000, and it says round to the nearest whole number. 13,519.
Professor, what did you get for the first one?
Okay. Testing. I'm back. I didn't realize my audio had gone out. Can you hear me?
Yes, sir.
Okay, yeah, I think my audio went out. Just trying to get the image back. But yeah, those results were correct. I just want to make sure my image is being pushed. Okay, the audio is working. Just give it a moment. Can you see my desktop?
No, not yet.
Let me push it again. Stop the share and then share. Okay. Start the broadcast. Optimize the video. And we should be able to see my desktop. Can you see my desktop? No, not yet. Start the share. Start the broadcast. So no desktop?
No, sir.
Okay. Let's see. Super share the screen. I should be able to see you should be able to see my desktop.
No, sir.
I should be able to see my desktop. Still no desktop. Yeah. Let me just reboot this real quick. Come on. Should be able to see the desktop. Can you see my desktop at all?
No, sir.
You can see it?
No, sir.
Oh no.
Yes, sir.
You can see it?
No, sir.
Okay, are you able to see the whiteboard now?
Still no.
Let me try closing some stuff. Okay, are you able to see the whiteboard now?
Still no.
See the whiteboard.
Still no.
Okay, it looks like it's getting pushed now. Yeah, okay. Okay, that was an adventure. I just had to keep trying different stuff until it worked. Did you have any more that you wanted to go through, or how you feeling?
I still wanted to review the question that we were on because I still had because I was a bit confused on how you got your answer. You said it was like 2332 or something.
Yeah, can you see my screen?
Yeah, I can see your whiteboard.
Can you see the like writing and stuff?
Yeah.
Okay. So was this 7/3? Was this okay? The 7/3? How we got that?
Yeah.
So then the thing you had to keep in mind was that both of these units are in thousands of units, right? So 7/3 is what, 2 1/3? So 2.3 bar, right? Is that okay?
Yes.
So when you write this guy as a decimal, you're going to get 2.333333. But then you got to keep in mind that that's really 2.3333 thousand, right? So then I just moved the decimal three times to the right, and that's where this came from. Same thing with this 13. This is really in thousands of units. So I went 1, 2, 3. And then it said also round to the nearest whole number. So it was 13,519. The nearest whole number is going to be 519. So basically it's saying produce and sell 2,333 units, and we'll get a maximum profit of approximately $13,519. So basically, I just said times 1,000 times 1,000.
Okay.
Mm-hmm.
When your answer, you just put 2,333 comma 13,518 point.
It asks two different questions. So it said the production level for the maximum profit, that was the 2,333 units, and then the actual profit itself was the $13,519.
Okay, so the production level was 2,300 unit, 333 units, and the actual profit was
$13,519. Yeah,
okay. So because you rounded to the whole number.
nearest whole number. Yeah.
Okay.
Yep. Today's Wednesday. It's trash day.
Okay, I see it.
Mm-hmm.
And more that I kind of want to go over.
Yeah, sure.
Okay, I sent you two problems.
Okay.
I just sent you three problems actually.
Share. Okay, this looks interesting. So it says a rectangular box with a volume of 80 cubic feet is to be constructed with a square base and a top. Okay. The cost per square foot at the bottom is 15 cents. For the top is 10 cents, and for the size is 2.5. What dimensions will minimize the cost? Okay, so we need to basically do a cost function based on one of these variables. It says the cost per square foot for the bottom, and for the top is 10 cents. What area, what dimensions will minimize the cost? Okay. Let's get a copy of this. And so we just need to get a cost function. Once we get our cost function, then I think we'll be okay. Let me copy and delete. Here, let's paste. Oh, let's cut. Down here. Paste. I think we're okay. Seems like I think it's where we left off. Okay, so we'll take it here. Come on. All right. So let's see if we can get the cost in terms of X. So let me see. We have a rectangular box that has this volume. We want to minimize the cost, right? So our goal is to minimize our C of X. So let me think. The cost per square foot for the bottom is this, for the top is this, and for the sides are this. What dimensions will minimize the cost? Okay, so we have that information on the volume, right? So we want to minimize the costs where our X and Y are positive, such that what? How can we express the volume? So the volume of this box is going to be what? Length times width times height. So our volume is going to be what? X times Y. Is that okay? Length times width times height.
Yeah.
Okay. And we're given the volume, right? We're also given that the volume is what? 80 cubic feet. So you see how this is kind of lining up to the one we just did a moment ago? Right? So we want to minimize the costs given that X and Y are positive such that X squared times Y equals 80. This is the exact same as one we did a moment ago. It's just a different context. So let's solve for Y in terms of X, right? So if we solve for Y in terms of X, we're going to get Y equals 80 divided by X squared, okay? Okay. So now for the cost of this guy, we have what? A total of 6 faces. We got the base, the 4 sides, and the top, right? So then let's create a cost function. So our cost, I'm gonna kind of write it like this. So we have the base, the cost of the base plus the cost of the 4 sides plus the cost of the top. All right. So the base, let me see, square base. The cost per square foot. Cost per square foot. Morehouse. 15 cents. Okay. So then the area of the base is going to be what? X squared. So we take the area, that's going to give us, you know, the area, and then, you know, square feet, but then we got to say times the, what is it? 15 cents per, the cost per square foot is 15 cents, right? So then we're going to capture that by saying 0.15. I think this is going to work. 0.15 times X squared. I think that's okay. So then if we consider one side is going to be X times Y, the area, right? That's going to give us the square area. So, and we said that Y is 80 over X. Let me write that a little bit better. 80 over X squared. And we said times X. That's for one side, but we have 4 sides, so we're going to multiply that by 4. So it's going to be a 4x. And then we need to capture the bottom for the top and for the sides. Is that per side or is that for all 4 sides? I guess that's the cost per square foot for the sides, right? So we're just going to say this times. Is that per side or for all 4 sides? For the sides. Only thing I'm not sure, cost per square foot. Well, this is the total square foot of the sides. And so we'll just say times the 2.5 cents. So you know, that'll capture the cost for the total sides. So 2.5 is going to be what? 0.025. All right. So that should take care of the cost of the sides. And then for the top, the bottom, the top is 10 cents. And the area of the top is, I think, x squared, just like the first part. If I can get my device to work. Yeah, x squared. So this should, I feel confident in this cost function, right? This is our cost function based on one variable, right? 15 cents for the bottom, 2.5 cents per square foot for the sides, and then 10 cents for the top, okay? And the goal is to minimize this. So in order to minimize it, we got to look at, let's simplify this down some because we can simplify this a lot. 0.15 plus 0.1 is going to be 0.25. So 0.25 x squared. Right here, this x turns this into a 1. Hey Siri, what's 0.025 times 4?
0.025 times 4 is 0.1.
So 0.1, that's going to be an 8. 80. So I think it's just 8, right? Hey Siri, what's 80 times 0.1?
80 times 0.1 is 8.
Okay, so that is just going to be plus, nope, right here. That's going to be plus 8 over x. I think this is our cost function. All right, I feel good about this. We simplified and combined like terms. So then in order to minimize this guy, again, we're going to look at the first derivative. All right, so this is just a simplified cost function based on how we set it up. In order to minimize, we're going to look at C prime. It was at 50. So 0.5x. If that's x to the minus 1, that's going to become minus 8x to the minus 2. Okay. So then we want to set this to 0 and solve any x that makes either this 0 or undefined. Okay. So what we have 0.5x minus 8 over x squared equals 0. What I'm going to do is combine the fractions to get a common denominator, you know, that kind of thing, get it into like one fraction. So what I'm going to do is multiply this first term by 1 in the form of x squared over x squared. I'm going to multiply by 1 like that. Okay. So then when I do this, we'll get 0.5 x cubed minus 8 over x squared equals 0. Okay. So then our critical value is going to be any x that makes either the numerator or the denominator 0. Right. So we're going to set the top and the bottom. We're going to set each part to 0 and solve. Okay. So then we're going to have this 0.5 x cubed minus 8. We're going to set that to 0 and solve. We're going to say or x squared equals 0. Okay. So from the first one, if we solve, if we add, you get 0.5 x cubed equals 8. Multiply both sides by 2. X cubed equals what, 16. Take the cube root. Because 2 times 2 is 4 times 2 is 8. So x is going to be, that's what, 8 times 2, cube root of 8. So that's going to be 2 times the cube root of 2. Okay. And then from the right, we get x equals 0. Okay. So are we doing a cost function? Come on. Okay, we're doing why does it C? Oh yeah, cost function, right? We want to minimize the cost. So obviously the x equals 0 doesn't make sense in the context, right? Because you wouldn't do a side length you wouldn't do a side of length 0. So our candidate is this 2 times the cube root of 2. Okay. So we want to confirm that it is indeed a minimum, right? So we got our 2 cube root of 2. Cube root of 2. Hey Siri, what's 2 times the cube root of 2?
2 times cube root of 2 is approximately 2.5198.
So this is approximately 2.5198, right? So left of that, we can choose something like, so we want to look at this in our C prime. This should be 0 in our derivative. So something to the left of this 2.5 would be like 0. If we plug in 0 into C prime, I think it can't be 0 because it makes part of it undefined. So let's try when x is 1. If we plug in when x is 1, we get a half. 1/2 minus 8 looks like we get a negative result. Right? So when we plug in 1, come on. When we plug in 1, we get a negative result, which implies that our original function is decreasing. Something to the right of this would be something like 3. If we plug 3 into the first derivative, we took the derivative, yeah. When we plug 3 into the first derivative, we get what, 3 over 2 minus 8 over 9. That's a positive number, right? Because 8 over 9 is less than 1, 3 over 2 is larger than 1. So we get a positive result. So we plug something in on the right-hand side, we got a positive result. So that means the original function is increasing. So because we go from decreasing to increasing, that confirms that this is indeed a minimum value. So the minimum occurs at that x value, let's see, and the minimum cost, right? So
Professor,
yes.
so you plugged in a number that's less than 2.5198 into C
We
prime,
plugged it in. Yep.
and it gives you a
And we got
negative.
it. Yep. And then we did the same thing on the right side. So I plugged in 3, got a positive result. So that means the original function is going from decreasing to increasing. That confirms our minimum. We need to find the corresponding y from the cost function, right? So let me try to wrap this one up and then we can go back. It's just my device is like kind of throwing a tantrum a little bit. Where's our cost function? Right there, right? So we want to plug in this x into the cost function to get the actual minimum cost. To see what does it cost to like, what is the actual minimum cost to do this project, right? So where'd it go? Maybe I think I just need to do another one. Let's go full screen. So like this, come on, don't freeze, just work. Oh, I think it froze. Come on. Oh, my device. Can we close this out? Do something, just go away. Come on. You can do it, I believe in you. No, that's not what I want. Can you just go this way or something? No. Oh, this thing is so the tantrum. Come on. Just go away. See, I'm hesitant. Like if I click too much, we'll lose our image again, which is what I'm trying to avoid. All right. I don't know how I got rid of it last time. I think I just need to restart my device. I think that's part of it. Why it's throwing such a tantrum. Come on. Okay, I'm gonna just try to work with this for now. Here. Nope, I just wanna come on. Yeah, I don't know how to get rid of that bar. It's just gonna have to be there for now. Okay. Let's get rid of this. Let's go to our y equals, get rid of all of this. And let's put our cost function that we got in here. All right. Okay. This guy right here. There we go. It just went away on its own. I didn't even do anything. So the cost function that we got was this 0.25 x squared plus 8 over x. Okay. Okay. So then we want to find the cost when we plug in 2 times the cube root of 2. So we're going to go to variables, calling it function, 2 times 2 to the power of a third. $4.76, is that right? Okay, we're just gonna submit it and see if it works. This one. Okay, it's 2 times the cube root of 2. So the length of one side of the base is we got round to 1 decimal place as needed. Okay, I think it's like 2.5. Yeah, we'll try 2.5. 2.5 feet. The height of the box. So now we got our x. We need to go back and find y. So way back at the beginning, we said y was 80 divided by x squared. So we're going to say 80 divided by, now the x that we got was 2 times 2 to the power of a third. 2 cube root of 2. And we want to say, we want to square all of that. Okay. So the height we got was 12.6 feet. That seems, yeah, I guess so. 12.6 feet.
How'd you get the height?
From the y from the beginning. We plugged in the x that we found into, we had 80 divided by x squared, y equals 80 divided by x squared, 12.6 feet. Let me submit this first to just make sure that it's right, and then we'll go from there. Okay, I'll check. Yeah. Is that okay? That was interesting.
You said you plugged in the 2.5.
Yeah, so y in terms of x, we got that y equals 80 divided by. Yeah, but I plugged in the exact. I didn't plug in 2.5. I plugged in 2 times the cube root of 2 into that. Because when you're doing these calculations, you want to keep it as exact as possible until the very end. If you start plugging in rounded results into your calculations, anything based on the rounded result is going to be even more skewed. So you want to do the best you can to try to be as exact as possible until you submit your answer.
So it's 80 over 2 times the cube root of 2 squared.
Yeah, and like that's what I typed in my calculator. But, you know, and that takes effort. Because you had to keep your parentheses proper. In this one, I couldn't do cube root, so I said 2 times 2 to the power of 1/3. I used my parentheses properly, put the squared in there, and then I submitted it. You can kind of see it there.
Okay.
This is interesting. But yeah, this is the kind of stuff that we were doing in optimization in graduate school. The only difference is where we're doing these manually by hand, the next level is basically big data. Like say you had a whole bunch of data that you're trying to process and you're trying to a cost function. So you're taking these concepts that we're talking about here and backing it with like some coding. So you might be able to like write a program that can run certain processes to do these calculations, but for a whole bunch of data, right? That's the only difference. It's basically what we're doing here, just expand the concepts to larger data sets. And then if you could do that, now you're primed for like industry and you can make decent money, like 6 figures easy. But yeah, if you can kind of follow all of this stuff, not many people can follow this or have the patience to follow it. People can do it, but just to have the patience to do that, you're a candidate for like being able to do things that other people can't do. So therefore, you'll get things that other people can't get, if you catch my drift. Like you should, like if you can just keep going with this as far as you can, just, but this is optimization. This is like industry stuff. Like pharmaceutical companies use information like this and processing the data from their patients. Tech companies, like so many people use this stuff for big money. You just got to dig and kind of get through some of the gunk of society, but you can definitely do some big things with this kind of stuff. But yeah, this is optimization. This is a topic I really enjoyed in graduate school. I could have gone further with it, and I still can, but I'm just like, man, I'm just kind of being like that about it, just being a baby. I need to just stop being a baby and just go try. Okay, I think you did some more. Let me pull up the next one. I think these two might be the last. We'll see how I feel after them. So I am starting to feel it. We're gonna pull up. You went there. Can we close out that tab? Let's close out that tab. Let's get rid of this. Let's open this guy. All right, let's try that one more time. No, stop doing that. Let's just get rid of this whole thing. You're gonna behave like that. There it is. Yeah, I just want that going. All right, now let me see you open it. Okay, that's better. Oh, but that means I'm gonna have to pull up my calculator again and go through the whole thing. A retail outlet for a calculator sells 600 calculators a year. It costs $2 to store one calculator for a year. To reorder, there is a fixed cost of $6 plus this for each calculator. How many times per year should the store order calculators, and in what lot size and what order to minimize inventory cost? So again, we're just minimizing costs. We want to make a cost function. Let me see, should we do different parts for these? I'm going to give it a go. So first, let's see if we can get a proper cost function for this. We're going to copy and delete. Right here, let's paste. Yeah, that's bad business what they're doing. That's not a good idea. That's gonna hurt the school for real. Credibility. Okay, let's see what's going on here. So It says a retail outlet for calculators sells 600 calculators a year. Okay. So we're going to let X be the amount of calculators produced and sold. It costs $2 to store. So we have some different categories at play here. So we're making a cost function, right? We're going to let X be what it costs to store a calculator. So to store a calculator for a year, it costs $2. So we're going to let S be what it costs to the number of calculators stored. And again, that's going to cost $2. Okay. To reorder, there is a fixed cost of $6 plus $125 for each calculator. So to reorder, there's the fixed, so I'm going to say plus. There's the fixed cost of $6 plus the $125 for each calculator to reorder. So I'm going to let R be reordering one calculator. So S is storing one calculator, R is reordering one calculator, and that cost is $6 plus $1.25 per calculator. How many times per year should a store, let me see, they sell this many per year. It costs to store one calculator for a year. To reorder, there's a fixed cost of $6 plus this for each calculator. How many times per year should the store order, so reorder calculators, and how many in order to minimize the inventory costs? Let me think about this. 600. It costs to store one calculator for a year for each calculator. So if S is to store, let me think about this. So let me see, a retail outlet for calculators sells 600 calculators per year. Let me think about it. Because we need to get that parameter, right? We need to use that 600. How can we capture that 600 and get our other equation? How many times per year should the store order calculators, and what lot size to order in order to minimize the cost? Let's see. Okay, I'm gonna look at the in just a moment. Let's see what we got here. Right here. Give an example right here. Okay, first make a list of the variables and constants. Yes, let X be the lot size for each order. Okay. There's too many things going on here. Inventory in terms of X. Yes, I do need to change that. Inventory is just made up of yearly carrying costs and the yearly. Okay. So the storage plus the reordering cost. That's fine. The lot size costs $2 to store, right? So use the average. To have a representative expression for the amount of stock at one time in a period, use the average X over 2. This represents the average amount held in stock over the course of each time period. X over 2. $2 per unit. I wasn't thinking X over 2. So the number of items in storage and the cost is $2 per item, which is just going to be X. Okay. I'm going to come back to that. Write an expression for the reordering cost. Start with the number of orders in that must be made in order to sell a total of 900 calculators. Okay. Start with the number of orders that must be made in order to sell. So you got to order 900. Let me see. Then write an expression for the cost to order one in terms of X. and the cost per order. So therefore the reordering cost is this times that. So the number of orders and the cost per order. Right, that's the cost. So we kind of got that, but we missed that part. So then you put those two together. Okay, so some changes that we have to make, right? We're on the right track with the cost function, right? I think for the stocking, for the stocking, so we put S, we're trying to get everything in terms of X, right? So let's go back. I just want to kind of digest that a little bit more, right? So first make a list of the variables. Okay, that's fine. So the storage fees plus the reordering fees, right? So the lot size is the largest number ordered each reordering period. If X units are ordered each period, then during that time, somewhere between 0 and X units are in stock. Okay. To have a representative expression for the amount of stock at one time in the period, use the average X over 2. This represents the average amount held in stock over the course of each period. Where's that 2 coming from? A retail outlet sells 900. The cost to store one calculator for a year is this. In order to reorder for each calculator, how many times? This represents the average amount held in stock over the course of each time period. The yearly carrying cost is the storage cost per unit multiplied by the average number of items in storage. So then next, we write an expression for the reordering cost. Start with the number of orders in that must be made in order to sell 900 calculators.
Morehouse?
Let's see. Then write an expression for the cost of one order in terms of X. Because we got this part, right? The fixed cost plus that's the order to sell a total of 900 calculators. And what is this? Start with the number of orders in that must be made to sell a total of 900 calculators. What is X again? Let X be the lot size for each order. Reordering cost. I got to think about, let me see, then write an expression for the cost of one order in terms of X. That's fine. The total yearly reordering cost for the product of number of orders is this, and the cost per order is this. So the number of orders. So each year they sell 900 units. So a retail outlet for calculators sells 900 calculators per year. It costs $2. So this is an average, right? However many they order. Okay, that's fine. But I don't understand why the other one was 2. That's the only one I'm stuck on. Okay. And then the carrying and the reorder cost to find the total function of X. So the cost function, we got that one, we got that. Okay. So there's only one part that I'm like a little bit shaky on. Let me see this one. Where does this 2 right here come from? The yearly carrying cost is the storage cost per unit multiplied by the average number of items in storage. The average number of items in storage is X over 2, and the cost is $2 per item. It costs $2 to store one calculator for a year. Okay. Okay, so the most challenging thing here is setting up your cost function. We did get this part over here where we have the 4 plus, that part there. The 900 over X, that's the average right here. The number of orders that must be made to sell a total of 900 calculators. Yeah, if you're going to sell 900 calculators, then you need to order 900 calculators, right? So, or however many you're going to order based on whatever's left. But so that one kind of makes sense, right? So then that's the number of calculators ordered times the cost to reorder each one. And then the first part was the average number of items in storage was X over 2, and then the cost for keeping each item is $2 per item. Okay. So if we apply that to hours, let me see if that works. A retail outlet for calculator sells 600 per year. It costs $2 to store 1 per year. Okay. Okay. So I'm thinking that part might be the same, where it has a $2 to store 1 per year. So then you would have your X over 2 times, because the average amount in storage is just going to be X over 2 times $2 to store each item. So I think that part is the same. And then you can kind of just match them up, right? Instead of 900, I think ours was 600, right? 600 over X. And then, I think the rest of it kind of flows from there. It was just that initial setup. Let me kind of capture that. So on our example, our cost function, we said the average number in storage is going to be X over 2 times $2 for each unit in storage. And then the cost to reorder is going to be the number of units. The number of units you reorder times the cost to reorder each item. Yeah. So in our case, that's going to be up there, which is going to be the $1.25 for each order plus the fixed. I think this is the cost function. That's the thing there. I'm just going to get rid of this. Okay, I think this is our cost function. Let's go with this, and let's give it a go. All right. So now once we have our cost function, then it's kind of a repeat because we want to basically minimize the costs. Right. Let's go with it. So in order to minimize this guy, let's simplify it down first. We're going to get X. I feel like multiplying. Hey Siri, what's 600 times 1.25?
600 times 1.25 is 750.
So if we distribute, those are going to cancel. So we're going to say plus 750, 3,600. Okay. So then if we look at C prime, it's going to be a 1. That goes to 0. That's going to be a negative 3,600 X to the minus 2. Okay. And then if we set this to 0 and solve, let's see. Okay, so we can add that to both sides. We're going to get 3,600 over X squared equals 1. So then X squared equals 3,600. So then X equals, what is that, 60? I think the negative 60 doesn't make sense in the context, so we're just going to go with the positive 60. Yeah, 3,600. Okay. So 60. So number of lots in each category. We should verify that that's indeed a minimum. Okay. So if we look at the 60 on a number line, if we plug in like 0, let's plug in like 50, I guess. Into, can we plug in like 1? If we plug in 1, which is the number to the left, looks like we get a negative result, right? So then C prime, 0. On the left, we get a negative. And then on the right, something like 61. That's going to be a number smaller than 1. So then that's going to be a positive. Right. So then we can confirm that this is a minimum when X is 60. And we plug 60 into the original function to get the minimum cost. So to me, the most challenging thing there was setting it up properly. I don't know what happened. Great. All right, let's kind of go with it for now. And I think I need to this. Okay, this one. Let's clear, what y equals clear. So our cost function that we got, hopefully I did that right. I think so. X plus 750, 3600 over X. Okay. Let's quit, clear, calling that function. And we want to plug in when X is 60. So 870. Does that make sense? 870. That's okay. So that should be the minimum cost. Should order this many calculators this many times per year. Okay. Here. Let me see. The reorder, there it is. To reorder, to store. To minimize inventory costs. Let me kind of see how they applied it there. This one. Okay, so we got a result. The reorder size must be at least 1 and no more than the total number of calculators. That's right. 1 to 900. Okay. They got the same thing we got. They're just confirming that it's a max. Or it's a minimum anyway. 60 units, right? Okay. Okay. Find a number of times per year. So, okay, we'll get that. That's not a problem. Okay, 60. Okay. So we're going to say what? Our 600. So should order 60 calculators since we got 60 as well. And then I think we had 600 divided by 60, which was 10. 10 times per year. Okay, right here. Okay. We definitely should do another one of those, right? But I'm totally burnt. Let's try to do one more. Let me at least look at it. There should be questions on that one. We can try to go back through it if you want. But you saw what I did. I just like went to the viewing example and kind of matched them up. The challenge there was setting up the cost function. You know what I mean? We're going to kind of let that be for now. Let me try to pull up this last one because I think I'm about at my limit. Oh, right here. Are you still there? I felt like I lost somebody.
Yeah.
Oh, you still there? Okay. Let me see. An open top cylindrical containers have a volume. Okay, let's try this one real quick. I feel like there should be questions on that one. Yeah, you saw what I did. I just kind of mashed it up. Why do you keep doing that? Let me get rid of this. Try to do that. Ooh. We can go back to that one. Let me just try to look at this last one, and then we can kind of go back and forth as needed. It says an open top cylindrical containers to have a volume of this. What dimensions, radius, and height will minimize the surface area? Okay. A cylindrical container. Okay, let's give this one a go. So I feel like I can do this one. Let's go like this. Get a copy. Come on. Like this. Oh, come on. Right there. Copy and delete. Okay. Where's my image? All right. So a cylinder, right? An open top cylinder container is to have a volume of this. What dimensions will minimize the surface area? Okay. So, we have like circle or this kind of shape. Let's copy. Let's paste. Okay. Mm-mm. Okay. So that dash means it's like behind. Okay. Radius. It has the volume is what, 512? Cubic centimeters, right?
Yep.
What dimensions, radius, and height will minimize the surface area? All right. Okay. What else do we have? We're trying to do surface area. Okay. So the radius, let's see. I kind of want to just let the radius be X. I'm going to let this be our X. And then we also have the height. Okay. So now with a cylinder, with this kind of image, right? The base, the simple shape of the base is a circle. Cylindrical, yeah. It should be a circle, right? The base should be a circle. So the area of the base is going to be what? Pi or pi x squared. like pi r squared. Now the height, if you were to like cut, cut along the side of the item and open this up and lay the wall rectangle, where one side is going to be H circle.
Professor, Professor, are you there? Because I can't hear you. Professor, are you saying something? Because I can't hear you. Professor, are you there? Because I can't hear you.
Yeah, I got all the way almost to the end. That's when I realized that you couldn't hear me because I kept asking. I was like, "Why isn't he responding?" I'll have to go back and just can you hear me now?
Yes, sir.
Yeah, I'm gonna have to just go back and walk. Yeah, I got all the way almost to the end. That's when I realized. 'Cause I kept asking. I was like, I'll have to go back. Can you hear me now? Yes, sir. Okay. So like now we're running into the image is being pushed. Now the audio's not working. That's like the second time that happened. Let me just make sure my image is being pushed. I guess I need to make sure the audio is working too. So right now. Oh, so now you can't see my image, man. Come on, Zoom. Ugh. All right. I guess I'm gonna just have to redo that one because my audio wasn't going through. Stop this. Share. Okay, I think if once I get this image to work, what I'm gonna do is just kind of piggyback on what I already have written and just kind of walk through it. But first, I got to get this image to show. Now, what did I do last time? That seemed like it worked. Oh, I know what I did. Okay. Stop this. Share the screen. Okay, start the broadcast. So what I did different last time that seemed like it worked is if I go like this, pull it from here. Come on. There it is. And then go like this. That seemed like it worked. Okay, that's a good omen. I can see it there. Okay, let's see. Yeah, I can see it. Okay, we're gonna go with that. Okay. So I think what I'm gonna do is finish it out and then just kind of recap because I know my audio wasn't picking up on my audio. So I'm just gonna kind of pick up where I left off, finish it, and then I'll just kind of do a recap. Okay.
Okay.
So let me just kind of wrap this up and then the other one. Yeah, that's all right. Let's see. So we're just trying to crunch that number. So we're going to say parentheses 512 over pi to the power of 1/3. Okay. Let me think. What are we doing? What are we doing? Surface area x, so the radius. Then round to 2 decimal places. 5.46 is our radius. Come on. So that's approximately 1.46 centimeters. Okay. Then for the height, right there. So can I just store that? I'm gonna store it as like alpha A. Okay. So then the height I'm gonna do 512 divided by parentheses pi times alpha A squared. Okay. Oh, we get the same, the height and the radius are the same? Hmm. Okay. So I got that the height and the radius are the same. Let me just see if that works, if that's actually correct. And then we can do a recap and kind of go through the work. And the height is the same. Oh, this thing is so nuanced. Turn this off. And it wasn't always like that. It's just like when I do updates and it just sends everything into a tizzy. 5.46. I'm just going to put 5.46 for both. It's really not designed for iOS, but I've somehow made it work. Okay, so let's walk back through what happened. Can you hear me okay?
Yes, sir.
Okay. All right. So let's just do the best we can. Okay. So back from the beginning, right? So we had a open top cylindrical container, right? A cylinder. So the basic shape for the cylinder, you have the two circles, circular base, circular top, and then with the side. It says it has a volume of 512, so you see it here. And then it says what dimensions for the radius and the height will minimize the surface area, right? So our goal was to minimize the surface area. So surface area, well, it has an open top, so there's nothing on top, right? But the bottom is a circle, right? And so the area of a circle is pi r squared. You see it right here. And instead of putting r, I put x, right? So this is the base, the area of the base.
Okay.
And then for the side, now if you were to cut the side like this and then open it up and lay it flat, it's going to make a rectangle, right? Where the side of the rectangle is going to be h, and the other side of the rectangle is going to be this guy here, which is actually the circumference of the circle. So then if you have a rectangle that's h by the circumference, then the area is going to be right here, the h times the circumference. So then surface area, all I did was to say the area of the base plus the area of the side. Let me say that one more time. So for the surface area in this context, I said the area of the base plus the area of the side. Okay. So then from there, I think we okay. So in order to calculate this, we wanted surface area in terms of the radius only. Right now we have it in terms of the radius and the height. So we needed to find an expression for the height in terms of the radius. So then that's where we come over here. That's where we use the volume. So the volume of the cylinder is basically the area of the base times the height. So that's pi r squared times the height. So then from here, and we were also given that the volume was 512 cubic centimeters. So then from there, we can solve for h, and we solve for h and we get this guy. Okay. So then we want to plug this h into our surface area formula, and that's where this came from. Let me kind of stop right there. Is this okay up to this point?
So you said that the h times the circumference, that's the area of the side when you cut the cylinder like in half.
Yeah, if you were to open it up, right? Like kind of cut one side and open it and lay it flat, it's going to make a rectangle where one side of the rectangle is the height. The other side of the rectangle comes from the circumference of the circular base. And so we capture that height times the circumference.
Okay.
So then from there, we wanted the height in terms of the radius. So then we use the volume to get this guy. So now after using the volume, we were able to get the height in terms of the radius. So now the whole point is we want to express the surface area in terms of one variable alone so that we can kind of move forward. So we were able to express the surface area in terms of the radius. I just called the radius x, but I could have easily called it r, right? All right, so now that we have the surface area in terms of one variable, I think I like expanded, simplified, combined like terms. So I just rewrote it here so I can have some more space. And then I just combined like terms and simplify. I think these pi's canceled each other out. We had two x's on bottom and one x on top. And so it's simplified down to this guy. And then from here, is it okay up to this point, up to here?
Yes.
So then from there, once we kind of simplified our objective function, then to find the objective, we look at the first derivative. So we said d by dx of our surface area. Basically, take the derivative. We get this guy for the first term and this for the second term. So then once we have the first derivative, we need to find those values of x to either make it 0 or undefined, right? So I'm a fan of, whenever I have a fraction, I like to get a common denominator and get it in this form. I'm more confident in this form than anything else, right? That's just me. I want to say that there are other ways to go about it, but this is what I'm comfortable with, so that's why I did it this way. So once I got it in this form, then all I did, you're going to find any x that makes either the numerator 0 or the denominator 0. And so I basically say each one is 0. Here's me setting the numerator to 0 and solving. Now with that denominator, the result there was going to be x equals 0. But if x is the radius, it doesn't make sense to have a radius of 0 in this context. So I didn't even bother with that one because I knew that was just going to give me something that I couldn't use, that was outside of the context or outside of our domain. So then I just focused on this guy on the left. And I solved for x from there. Added my 1024, divided both sides by 2, divided both sides by pi, and then take the cube root, and that's where this guy came from. And then that's approximately 5.46. I tried to keep it as exact as possible until the very end. And then I think it said to round to 2 decimal places. So the question was asking what dimensions of the cylinder are going to minimize the surface area. So this is the radius that's going to minimize the surface area. I went back and plugged this into our height function back up here to find the height. Once I had that x, I plugged it in, and it just happened to be the same number. So they both happen to be, the radius along with the height both happen to be this 5.46 centimeters. So I definitely did not have a flawless victory today, but we made it to the end, and those numbers worked. We've already checked it, so it actually did work. Okay. I think we're gonna have to Try some more a little bit later. It's definitely past my bedtime.
Yeah.
Okay, that was pretty good though. That was really good. I definitely got stumped a little bit on some parts there, but I think we found our way. Okay, so just kind of keep working for the just kind of do what you feel like you need to do for the night. If you get tired or feel weird, just turn it off. Just put it down for a while. Go to sleep, get some rest. But I found out like when I was studying math, the best time for me to think about this stuff was when I first wake up. That's just me, and I would be waking up at like 2 and 3 in the morning, and I'm kind of a night owl, and I still do that to this day. Like I'll be up at those hours, and so that's when I'm most productive. But that's just me. Okay. Did you want to ask any other questions before we kind of call it a day?
No, because I got a lot more other questions, but we can work on it like tomorrow if that's okay.
Okay, yeah, we'll try again another time. All right.
Yeah.
Okay. Well, enjoy your evening, and we'll see you later.
All right, you too. Bye, Professor.
Peace.